4.5 billion years ago, when the solar system was just beginning to take its first breath, a planet formed first inside a disk of dust, ice, and the ashes of dead stars. It was 11 times the diameter of Earth, and so massive that even adding up all the other planets still wouldn't be enough to match it. Back when the sun's fire was still relatively quiet, a planet so huge and heavy that it helped shape the structure of the solar system earned the title King of the Planets, Jupiter. Deep inside this giant world, a strange secret is hiding, one that our everyday intuition can't easily explain. For a long time, scientists have debated how Jupiter grew into such a colossal planet and what its core actually looks like. The two leading ideas are known as the core accretion model and the gravitational instability model. In the core accretion model, a planet is thought to grow from a small seed. Ice and rock within the protoplanetary nebula gradually clump together, building up a larger and larger body. Once that heavy core forms, its strong gravity pulls in the surrounding hydrogen and helium gas. That small core rapidly swells into an enormous ball of gas, eventually becoming the giant planet we call Jupiter. In fact, observations of exoplanets have found many gas giants that appear to have solid cores, lending strong support to this idea. But there is a major problem with this model. The gas in a protoplanetary disk disappears in just 3 to 5 million years. If a core at least 10 times the mass of Earth doesn't form within that short window, it can't capture and hold on to the gas. To explain this, scientists have proposed a new idea called pebble accretion. But whether this really works in practice has remained an unsolved puzzle. Other researchers instead put forward the gravitational instability model. In this picture, a huge cloud of gas collapses under its own gravity, condensing directly into a massive clump of gas. Gas clouds have mass too, of course. Normally, inward pulling gravity and the outward pressure from heat balance each other. But if the cloud grows larger and at the same time cools down, that balance can be broken. Once it passes a critical point, the cloud contracts rapidly and a high-density clump forms at the center. In this scenario, a solid core isn't necessary. On top of that, the whole process is very fast, so it neatly fixes the main weakness of the core accretion model. But this model has its own weakness as well. For such a dramatic collapse to happen, the cloud has to be in an environment where it can keep cooling, far from the sun in a much colder region of space. The problem is that Jupiter's current orbit doesn't fit that description. So some scientists argue that if the gravitational instability model is right, Jupiter must have been born much farther from the sun and later migrated inward to where it is today. In the end, neither hypothesis had any decisive evidence for a long time. Jupiter was too far away, and its interior was hidden behind thick clouds. Peering deep inside it from afar was almost impossible, at least until now. On August 5, 2011, NASA's Juno spacecraft left Earth. Using Earth's gravity as a stepping stone, it flew roughly 2.8 billion kilometers and finally entered orbit around Jupiter on July 5, 2016. Juno had a single mission: to examine Jupiter's interior in detail, or to be more precise, to listen to it. Juno is not just a simple observation satellite. The entire spacecraft functions as an ultra-precise gravity scanner. The key is gravity. Jupiter's interior is not uniform. Some regions are denser, while others are less dense. Naturally, the strength of gravity also varies slightly from place to place. Juno can detect these tiny differences, and the way it does this is simple, but very intriguing. Radio antennas on Earth send signals at a fixed frequency to Juno, and Juno simply reflects those signals back. If Juno's speed changes even slightly under Jupiter's gravity, the frequency of the returning radio waves shifts by a tiny amount. This is the Doppler effect. An ambulance siren sounds different when it approaches you and when it moves away. The underlying principle is exactly the same. As Juno orbits Jupiter, its speed becomes ever so slightly faster in some regions and slightly slower in others, depending on how mass is distributed inside the planet. Here, ever so slightly means about 0.01 millimeters per second, an extremely tiny change, roughly the distance a strand of hair grows in a tenth of a second. From Earth, scientists can analyze the resulting minuscule frequency shifts in real time and use them to draw an extremely detailed gravity map of Jupiter. As Juno made dozens of close passes over Jupiter's polar regions, that map gradually came into sharper focus. The heart of Jupiter was finally beginning to reveal its shape. And when scientists finally saw the results, they were stunned. There was clearly a core at the center of Jupiter, but it looked nothing like any form we had imagined. It was neither solid nor liquid, and there was no sharp boundary at the center. Instead, it seemed to be spread out like a kind of haze, so strange that calling it a core hardly felt right. Scientists now refer to it as a diluted core. This diluted core core was about 70,000 kilometers across, roughly half the diameter of Jupiter. This meant we would have to rewrite our planet formation models from the ground up. How could a structure like this possibly have formed? The first idea that came to mind was the collision hypothesis. In the chaotic early solar system, when unfinished planets were constantly crashing into one another, perhaps Jupiter's solid core was shattered in a giant impact and mixed into its surrounding layers of gas. It sounded plausible, a remarkably attractive explanation, but supercomputer simulations told a very different story. Right after the impact, the interior was mixed, but as time passed, the heavy elements sank back down to the center. In the end, the core once again developed a clear, sharp boundary. Scientists were left stumped. None of their existing ideas could explain such a bizarre core. Unexpectedly, the crucial clue appeared not on Jupiter, but on another planet. Scientists studying Saturn's rings discovered that the tiny waves seen in the rings were caused by vibrations from deep inside Saturn itself, a kind of planetary seismic wave. And when they combined those wave measurements with gravity data collected by the Cassini-Huygens spacecraft, a remarkable result emerged. They found that inside Saturn there was a vast region where convection simply didn't occur. What does that actually mean? Normally, heat inside a planet is constantly trying to escape outward. On Earth, hot material rises while cooler material sinks, driving continuous convection. But inside Saturn, there was a zone where this kind of convection had completely shut down. The material there was arranged in immiscible layers, whose compositions refused to mix. Like oil floating on water, the heavier elements slowly settled toward the interior, while the lighter ones spread outward. That's right, Saturn too turned out to have a diluted core, just like Jupiter. At first, scientists had assumed Jupiter's diluted core was the result of some rare accident, an exceptional one-off event. In fact, it may be the standard way giant gas planets are born, their natural internal architecture. Of course, we still can't give a definitive answer, but one thing is clear. The planet models we once relied on were far too simple and incomplete. Scientists are now building new planet formation models to explain how such a diluted core could form naturally. The hero behind this discovery, the Juno spacecraft, has been sending back hundreds of gigabytes of data on Jupiter and its moons, revealing a hidden corner of the cosmos to us. But its instruments are gradually reaching their limits. Before long, Juno will complete its final close flybys and then plunge into Jupiter's atmosphere. The only spacecraft ever to peer so deeply into the king of the planet's heart will itself become part of it, listening to its heartbeat until the last moment.